problem. Out there is the recursion that we had computed in the morning. If I want to find out the optimal solution to the lot sizing problem up to time t, the recursion that I can get is that I look at the preceding production time, the last production before time t, then I know that inventory before that time should have been 0, so I can split up the total cost to be the cost to come up to time u minus 1 plus the total cost to produce at time u all the demand that's required up to time t. And this is that cost. So the first step in trying to compute this thing is I have to get the p hat u in terms of the data that's given, which is f, p, h, and u. By definition, p hat of t is defined to be equal to p of t plus the sum of tau greater than equal to t of h of t, or h of tau. It's the production cost plus the inventory holding cost from that time all the way up to time capital T. So if you use that, you end up getting that the p hat corresponding to this data over here, I'm just going to put it on a different line to just save myself some space. P hat has these numbers 8, 7, 5, and 4. 8, 7, 5, and 4. And let's just verify. So the first one basically would take this number and add to it everything. So the sum of all the holding costs is 5 plus 3 is 8. The next number over here would be this number plus the sum of all of these guys, so that's 4 plus 3, 7, and so on. Okay, so it's just an addition of these things. And then we also need to compute the constant that is required to be subtracted out, and that constant turns out to be sum of t going from 1 to capital T of the holding cost times the sum of demands up to time t. So this is tau going from 1 to t of d tau. The formula that I gave in the notes is slightly different. It's just summed in a different order. Here, you use this formula. You look at the P2, which is 3, and add to it all the inventory holding costs from time 2 up to time capital T. So that's 3 plus 2 plus 1 plus 1. 4 plus 3, 7. Okay? It's from that time all the way up to the future. So for the first one, you will add up all the inventory costs. For the second one, only up from time 2 all the way up to time 4. For the third one, from time 3 and 4. And the fourth one is just this plus that. Okay, and that's how you get those numbers. And this constant turns out to be 37. What do I care about this constant? At the end, when I'm trying to compute the optimum value of the cost, I have to subtract this constant out. All right? Okay, so here's the recursion, and let's start working with it. So what is V of 1? V of 1, remember, is the total cost of solving the optimum uncapacitated lot sizing problem for time 1. What is that going to be? That's by definition f of 1 plus p hat of 1 d1. And that turns out to be, if you work out the numbers, 28. Questions? Okay. V hat of 2, or V2, is going to be the maximum of two quantities, V of 0 plus f of 1 plus p hat of 1 plus d1 plus d2, or V of 1 plus f hat of 2 plus p hat of 2 d2. Now let's just try to figure out what's happening here. In this situation, where am I producing? We are producing at time 1 for both the demands d1 and d2. What about here? What's happening? Yeah, so we are producing the demand at 1, producing to meet the demand at 1, and again producing at 2 to meet the demand at 2. So the last production instant here is 2. So remember, this recursion goes from 1 to t. So the first element here corresponds to 1, meaning the last production epoch was time 1, in which case at time 1 I need to produce everything. This one says that the last production epoch was time 2, So up to time 1 I satisfy by producing at time 1, and then I produce at time 2 to satisfy the demand at time 2. This quantity here is nothing but 28 plus the extra, so this is nothing but, this is just a computational trick. This quantity is nothing but 28 plus p hat 1 d2. Just to reduce myself some computation, I can write it that way. And that is 28 plus whatever is f2 plus p hat 2 d2. If you compute the numbers, this turns out to be the maximum, or sorry, I don't want maximum, I want minimum. I'm not maximizing my cost, I'm minimizing my cost. So minimum of, so that turns out to be the minimum of 60 and 76, which is 60. Okay. At this point, we also have to keep track of what was the optimum thing to do here. In the morning, when I talked about the recursion, we were just simply computing costs. We were not looking at the optimum decisions. Where are we going to produce? So here I have to keep track of the optimum production decision. This is the same thing as when we try to recover the shortest path by keeping track of what was the node that we came in from. So let's call D to be the decision at time 2. So it just keeps track of where was the last production epoch. So what is D2 in this case? What was the last production epoch? The optimum point to produce? 1. We'll need this to recover the optimum production, but for values we don't need it. Okay? What about V3? That's going to be the minimum of again the same quantities, V0 plus, now I'm going to assume that I'm going to produce at time 1 for everything. That is p hat of 1 times d1 plus d2 plus d3. The next one would going to be V1. That means I'm going to, the last production epoch was time 2. So before time 2 I accounted for by looking at V1. I'm going to produce at time 2, so I pay the fixed cost plus the variable cost. And how much will I produce at time 2? D2 plus D3. And finally, the last production epoch is at time 3 itself. So I'm going to pay the fixed cost plus the variable cost and produce only the product for D3. Okay, that's the recursion that I have to do. So if you work out these details, it turns out to be, how can we minimize these costs? One way to remember is this is nothing but this number plus P1 hat D3. So this is just again a computational trick. This whole expression is nothing but this expression, which is 60 plus P hat 1 D3. What about this expression? This expression is nothing but that expression plus P hat 2 D3. So that's 76 plus P hat 2 D3. And the last one I have to compute again. So in V hat 2 was 60 plus F3 plus P hat 3 D3. This is, yeah. So what I did was that this whole expression, this one, I just computed this quantity, whatever it was. Which one? P hat 1. P hat 1 is 8. It's not P, it's P hats. No, all the time, H tau all the way from time 1 to time 4. It's as if you produce and you hold up to the end of the horizon. All right? So these three numbers turn out to be the minimum of 100, 101, and, or sorry, 100, 111, and 101. And so the minimum quantity turns out to be 100. And what is the optimum decision at D3? 1. I still produce at 1. I produce at 1 for all the time horizon. All right? Any clarification so far? I'm just using the same, that recursion that we computed. All right. And the bottom, I'm going to do the same thing. You write out the same expressions, you will end up getting, because I don't think any of it will be visible, so I'm just going to put down the numbers and you can check this in your time. It's going to be the minimum. The first will be 108. The next would be 118. The next would be 106. And the next would be 112. This will correspond to producing at 1, producing at 2, 3, and 4. And the minimum of all of that turns out to be 106. Therefore, D4 is going to be equal to 3. All right? So now let's recover the optimum production cost. How would I get the optimum production now from here if I have all of this data? What am I going to produce and when? Basically, what I want a solution for is y and the x's. Remember, in my IP, I had the y's and the x's. This was telling me when am I producing, and this was telling me how much am I producing. So look at this data and let's try to recover. How are we going to recover? We work backwards. So if D4 is equal to 3, what does it tell me about Y4 and X4? 0. Y4 is equal to X4 is equal to 0. What is Y4 and X4? Y4 was the variable which just decided whether there is production at time 4 or not, and X4 decides how much was being produced at time 4. This last number here tells me that the optimum thing to do at time 4 is to actually produce at time 3. And therefore Y4 and X4 are equal to 0. Clearly Y3 is equal to 1 because I do produce at time 3. And how much do I produce? What is X3? D3 and D4. So I produce both for time 3 and for time 4, and what does that turn out to be in terms of numbers? 6. All right. What about, now what do I do? What about Y2 and X2? What do I do about that? How do I figure out what is the value of Y2 and X2?
But we consider D of 3 to be 1.
D of 3 is to be 1. So we recurse back from here. We said that the last production epoch is going to be 3 here. Okay? So then where do I have to check to see when will be the last? So okay, so what we want to figure out is that at this point, let's just do a network. It becomes a little bit easier. So what's happening is here's time 1, time 2, time 3, and time 4. At time 4, this is what we are saying. We are producing at time 3, both for time 3 and time 4. Now, in order to check back to the solutions in this area, do I have to look at D3 or do I have to look at D2? Does everybody agree that it should be D2 and not D3? Because if I'm producing at time 3 to suffice both 3 and 4, here's where the break in the problem occurs. There is no inventory going across. S2 is equal to 0. Therefore, in order to construct the optimum solution, I have to cross over this boundary to go to time 2 and then work backwards from there till the next break occurs. So what does it say about time 2? What's the optimum thing to do at time 2? Produce at 1. So what does it tell you about Y2 and X2? Zeros. And what about Y1? That's equal to 1. And what about X1? How much would you produce at time 1? D1 plus D2. And that turns out to be whatever it was. 6. All right? Okay. And what is the total cost? What is the optimum cost of production for this lot sizing problem? So it's 106, the number that you get here, minus this constant. So the total cost is going to be 106 minus 37, which turns out to be 69. Questions? Any clarifications? Things you didn't understand?
So what's the significance of d of 3 equal to 1?
D of so D tells you is what was the last point at which production occurred. So that tells me where is the break in which where the break occurred. So if D4 is equal to 3, it means that I produced at time 3 for both of these. So I know that this part of the problem is already solved. I know the optimal solution for this part. Then I know there is a break here, and this part of the problem is solved independent of whatever happened here. So if I go back here and ask myself, how much do I solve, what is the optimum solution for V2? That tells me that the optimum thing to produce is at 1, and then I can recover from there what the optimum solution is doing. So these D's are keeping track of where was the last production epoch. And once you know the last production epoch, you know the preceding point is where you have to go and check for optimality again, because there's a break in the problem right there. Question?
So why is D3 1?
Don't care. I don't know. Because at this level, which one?
D3.
D3. You're saying that 3.
So D3 is 1. D4 is equal to 3 is okay, but D3 equal to 1.
Let's just check. What does it say? So I'm going to produce at this point. Okay, so that's fine. Because of the future cost that happened at time 4, if you were only stopping at time 3, then the optimal thing would be to produce at time 1. If you wanted to go forward at time 4, then this optimum solution is no longer optimal. So basically at every stage of the game, so the question is, why is D3 equal to 1 and why is D4 equal to 3? And then we skipped this point altogether, is that what we are doing is solving the problem in stages. At this stage, we're simply asking the question, forget about what happens to the future. Just if you had just up to time 2 available, what is the best thing you're going to do? Then this stage we're asking up to time 3, whatever be the demand, what is the best thing you're going to do by looking at the demand only up to time 3? At the next stage you're going to say, what is the optimum solution when I'm going up to time 4? So if this demand is there, that could possibly change the decision about what happens in the past. And that's what happened in this particular case. This particular thing forced me to skip the product, to start producing at time 3, even though it's at this point itself, it's cheaper to produce at time 1.
So sir, so why are we saying that we are meeting the demand for 3 at, I mean, what if D of 3 is equal to 3? And
That's fine.
What's the difference going to be in the total solution?
Nothing. We skipped over this node altogether. Question?
Yeah, I just missed why the total cost is 69.
Oh, because there is this constant that we had to subtract out. So when we are keeping track of this addition, all it's doing is adding up the objective. And in order to get the objective back for the right one, I had to subtract out this constant. That's all. Okay. So the way to think about it is that we are solving this problem in stages. At every stage, we are finishing off the optimum solution up to that stage. So if there was no time 4, then this D3 would be important. It would tell me that produce everything at time 1 for the entire time horizon. But because there is another time horizon, time 4, I have to first start from time 4. I have to go backwards to figure out, in order to satisfy demands up to time 4, what am I going to do? It says produce at time 3. So once I've produced at time 3 is gone. Now I go one back to time 2 and figure out what is the best thing to do at time 2, and then go back and so on and so forth. So the solution of the future is going to affect the optimum solution, but up to a certain point I can compute out the optimum solution without looking at the future.
So it can never be that you're producing at 3 only to meet the demand at 4.
No. Any other questions? Okay. So this is sort of, so far we've done 3. In the homework you would have done 1 example of shortest paths. We did 1 in class about these companies. This is another one, and the homework or the final has basically another recursion in it. The thing to remember is that the crucial part is to get the recursion right, and once you have the recursion right, the way to recover the solution is to go recursing in one direction and construct the optimum solution in the reverse direction. In this case, we have come forward, and the optimum decision is going to be constructed by going backwards. If we had gone backwards, then the optimum decision would have been constructed coming forward. Okay? Let's see. Okay. So now the next topic that I want to talk about is relate, and all of the stuff that I'm going to say from now onwards in this lecture is not on the exam. But this is something that we would be needing in the next semester, so I might as well tell you. And give you an idea of why all of this stuff is important. And it's all to connect back to a story of linear programming. So far we have talked about, so in this course we talked about linear programming in the very beginning, then went to nonlinear, then went to integer, and now we're going to complete the full circle and show you that dynamic programming is nothing but linear programming in disguise. You would never want to solve a dynamic program by solving a linear program. It's more complex to solve a linear program than a dynamic program, but knowing the structure is important. And I'll show you one example of what happens when you know the structure in today's class, and we'll use it again and again in FE1. Okay, so here's the story. Let's look at the shortest path problems, and let's assume for the moment, in order to make our life simpler, that all of these costs, Cji, are positive, strictly positive, so that there is no negative cost cycle. I can really talk about shortest path looking at the recursion. The equivalence goes through even if there is negative costs, but it's easier to think in terms of positive costs and then worry about what happens when you have negative costs. This is what it's up. So if L sub I, what is that equation up there saying? If L sub I is the shortest path, or the length of the shortest path, to be very specific, from a source node S to node I, then this L sub I satisfies this recursion. There's no stages here. All I'm saying is that L sub I should have come to this node from some node. I could have directly come from the node S, or I could have come from some other node. So L sub I is in fact equal to the minimum over j taking values 1, 2 up through capital N of the shortest path up to node j plus the jump from Cj from j to I. Right? It's just simply saying if this is the shortest path, then it must satisfy that equation. Let's relax that. This particular thing implies that L sub I is less than equal to L sub j plus Cji, I going from 1, 2 up through n. Because L sub I is equal to the minimum, L sub I has to be less than equal to each of those terms. Then I claim that if I want the shortest path from node S to node D, so I want the shortest path from node S to node D. So D is a specific node that I'm after, which is this length is given by L sub D is in fact the solution of that linear program is equal to the maximum LD such that L sub I is less than equal to L sub j plus Cji, I taking values 1, 2 up through n, and j taking values 1, 2 up to n. And L sub s is equal to 0. So the important thing is that we were minimizing here, but there's a maximization sitting there. So what we are trying to do is push the L sub d as far as we can, keeping these constraints in mind. Okay?
What's our of S equal to 0?
Because this is the length of the shortest path from the source node to source node. That's 0. If you don't like L of s equal to 0, just remove that from the variable. This is basically saying L of s is not a variable if you set it equal to 0. So I claim that this shortest path problem is in fact equal to this. And you can check for yourself that if you take an optimum solution here and put it here, it will satisfy the constraints. And similarly, take the optimum solution here and go back there, it will satisfy the constraints. So a dynamic program, we computed L sub I by using dynamic programming. The final solution, the optimum solution of a dynamic program, can be computed by solving a linear program. How many variables does this have? It has capital N variables and capital N squared constraints. Which means, and typically you would never want to solve that LP to get the value of the lengths. It's nice to know that in fact that dynamic program can be represented by a linear program, but in practice you would never solve the linear program to get the solution. It takes much more time to solve that. There are lots of matrix inversions going on in there. You have to use simplex or something of that sort. Here it's just addition and minimization. That's much easier than trying to compute inverses. Okay, if you take the dual of this linear program, then you end up getting a linear program which looks like that. So the dual of this linear program is given by minimization of sum of lambda I j, Cij, I going from 1 through capital N, j going from 1 through capital N, such that these constraints, so think of lambda ij as the flow along the arc ij. What is this constraint saying? This constraint is simply saying that the flow coming into any other node other than node S and node D is equal to 0. Whatever flow comes in must leave. If you look at node D, then a unit demand has to come in there. One unit of demand has to come in there. And since none of the other nodes are allowed to be source nodes, none of the other nodes are allowed to have flow coming in, the only node from which flow is going to come is going to be this node S. Now let's not worry about what happens to the optimum solution there. Let's talk about the optimum solution to this dual linear program. If this is the kind of linear program you are given, what will be the optimum solution? All it's saying, so here's the situation is this. You've got a node S here which has infinite supply. You can go along any possible node and you want to put down a supply of 1 unit at node D. The cost of any of these edges is Cij. How would you route the flow? What will be the direction? How would you move the flow from source node to the destination node if you want to minimize the total cost? You will take the shortest path. Since there are no capacity constraints on the flow, this is the same argument that we used in the morning to get that recursion going, that one or the other path will be shorter. Here, there are no capacity constraints. You can pump as much flow as you want along the path, which means that the cheapest way to deliver flow here would be, in fact, where? Would be along the shortest path. So all of these edges, say if this is the shortest path, would have a flow equal to 1, which means that the variables, those variables are strictly positive, which means that their corresponding constraints will be strictly equalities by complementary slackness, which means that you recover exactly that the shortest way to get here is to via there, the shortest way to get there is via here, and so on. Why do we care about this duality? We care about this LP representation because there is this notion of duality. What do I mean by duality? What I mean is that suppose let's keep this in mind, and then we'll go over to one more step about approximate dynamic programming and come back to this story. What do I want you to remember from here? I want you to remember that the shortest path which we could compute using dynamic programming is equivalent to a linear program. That linear program has a dual, and the linear program and its dual have equal values. Okay, so keep this in mind. Now let's go and introduce one more topic, and we'll connect these two topics at the end of the lecture. So one topic that I introduced just now, which is sort of left hanging, is that dP is equivalent to LP. And this should actually, if you think about it, you should worry a little bit about this. Why? Because look at the problem we just finished doing, the lot sizing problem. That lot sizing problem had integer variables in it. It had 0, 1 variables in it, right? And here I'm turning around and telling you that the dP is equivalent to LP. The problem that we began with when we were trying to solve that lot sizing problem was a mixed 0, 1 problem. It had 0, 1 variables and it has continuous variables. LPs can only have continuous variables. We solved that problem using dP, so I know that I can solve that problem using dynamic programming, but now I'm turning around and telling you that dynamic programming is in fact equal to linear programming. And this is the part that you should worry. How can it be true? I mean, there is something strange going on. Without a network, it doesn't matter. We can the uncapacited lot sizing problem had a network.
That's why it's...
Without a network, anything can be made into a shortest path. Anything in dynamic programming is shortest path. Once you have the states available, all you're doing is computing the shortest way or the longest way to get to that state. So whether you have a network or not, there is an implicit network. But that doesn't quite answer the question. Even on the network, you could have a network design problem, which has 0, 1 variables. That's not a linear program. So there's something else that happens. Think about it, and we don't really need to worry about it right now. When we finish all the story that I want to talk about today, we'll get to it. All right. The next idea that I want to introduce is that of approximate dynamic programming. This idea is quite important, and in fact, almost everything that happens in practice nowadays using dynamic programming happens in this domain, whether it be in transportation problems, whether it be in financial problems, whatever it is, people cannot do exact dynamic programming. So you have to do approximate. And I'm going to motivate that using this idea of an American option, but without a binomial tree. So what's happening is that you have time which is discrete, t equals 0, 1, 2, and so on, up to time capital T. So that's the exercise dates. We already know this expression for the option price. H of S tau is the payoff that you get when the stock price is ST. If the stock price is ST and you exercise, the payoff you get is HT. So the price of the option is the supremum over all stopping times tau greater than or equal to T of this quantity. Okay? So V of T is actually a function. It depends on the current stock price. When we were doing binomial trees, and this is what you've done in your homework, you compute this value for every node. Every node is a state. In a binomial tree, there can be only finite values for the stock prices, and you computed this number for every one of them. So in fact, this V of T is a function. It's a function for all possible stock prices. So there is a finite number of stock prices. You can compute the value of V of T in all of them. Now think of a situation where you're sitting at time t minus 1, and you're allowed a continuum of prices here. S is R plus. The stock price at time t belongs to R plus. But the payoff here is very clear. It's just H S of t. This is just a function. It's given. And if H confuses you, think of this function as just K minus ST positive part. Let's say that is what the function is. Okay? Now, if I wanted to do dynamic programming and I wanted to figure out what is the price of the option at time t equal to 0, I have to compute its value here for all prices. I have to compute Vt minus 1s for all possible values of the stock price. Little s. For the binomial tree, this is doable. because at most at time t minus 1 you will have at most t minus 1 values, t minus 1 different values. At time 0 you have 1, at time 1 you have 2, and so on. So if this is what the binomial tree is doing, you know that at this point, not t minus 1, but at most t values are there. So this is not a big problem. You can compute this function for all of those capital T values and you're done. If on the other hand, the stock price is not a binomial tree, you're still looking at a discrete time process, but the stock could take a continuous set of values, then in order to work with my dynamic program, I have to compute this for all values of S. That's not doable. You cannot compute it for all values of S. Sometimes, and this is the place where dynamic programming is used analytically, you can compute a function. You can explicitly compute out what this function is. If you're lucky, you get a good answer. If you're unlucky, which is most of the case, you won't get an explicit solution. So given a value of S, you can compute what this is, but you cannot write it out as an explicit function. Approximate dynamic programming rescues you from this particular setting. When you do not know, you have to compute this entire function. You don't know what that function looks like. So somehow you want to reduce the problem of computing this function to computing finite set of numbers. When we did the dynamic programming with the binomial tree, we just computed capital T numbers. What I want to do is do the same thing here. I want to give up on exactness. I'm going to give up and say, look, I can't compute the exact value. Maybe I'm only going to compute an approximate value, but I want to compute that approximate value by just computing a finite set of numbers. And the way to do it is via, actually there's one thing missing, let's just do that as well. So basically now what I want to do is reduce the dimensionality of the problem. Reduce this problem to computing some vector. Let's call it R. Just some vector, and I'll motivate this in a moment. How do I get this vector? But before we go further, there is a little innovation that people did, and that comes from consideration of bias in estimating certain things. You'll see this Q-value iteration business when you do the Markov Monte Carlo simulation course. And when is that going to be? In the fall or the spring? Fall. So when you do Monte Carlo simulation, you will see that if you simulate things one way, you get bias, and if you simulate it another way, you don't get the bias. And this Q-value iteration, which is equivalent to dynamic programming, turns out to not give bias, whereas the other one does give bias. For our purposes, we'll just show that they are equivalent. Numerically, they are not equivalent because one is better than the other. Analytically, they are the same. So here's what we had. We had a dynamic programming recursion which said that V T of S is equal to the maximum of two quantities, K minus S positive part, and here I'm assuming that H of S is in fact K minus S. Exercise now, or look at the expected value of V T plus 1 of S T plus 1, given that S of T is equal to S. And if you want to, you can take e to the minus r here. Right? This is what dynamic programming recursion was. This is what we did on, when was it? Last Thursday. Cost of exercising right now, or the revenue from exercising right now. This is just a fancy way of writing that if today's price is little s, look at the expected value of st plus 1 given this and see what revenue you get from there. If you continue, that's the expected revenue you can get. If you just give it up right now, that's the first component gives you the revenue. So here what you end up getting is define this thing to be qt of s. Let's not worry about qt vt plus 1, just define this to be qt of s. This is the conditional. This is the revenue that you get from not exercising right now and just continuing. So qt is the revenue from continuing. So qt also satisfies another recursion, qt of x or s is in fact equal to the expected value of e to the minus r, and what I'm doing is I'm replacing this quantity by its iteration. It's the e to the minus r of the maximum of k minus st plus 1 positive part and qt plus 1 of st plus 1. All I did was replaced this quantity here is nothing but the replacement of an expression for vt plus 1. Again, the point to remember right now is don't focus too much on how I got this recursion. So there is a recursion available. The reason we want to get this recursion, for those of you who are statistically minded, is that the maximization is inside the expectation. Here the maximization is outside the expectation. That causes problems when you're trying to estimate something using sample data. One is better than the other because it does not introduce bias. And that's why people use this, not that. But for our purposes, for the discussion that I want to talk about right now, Vt and Qt are equivalent. If I can compute Qt, I can tell you whether I'm going to exercise or not. If Qt is greater than this value, I'll exercise and not exercise, and if Qt is less than this value, I will exercise. So in terms of trying to compute the optimum solution, I don't really care whether I compute this or I compute that. The next step, which is this story, how do I reduce this problem? So what people have tried is that they've assumed that Qt of x is actually given by a set of basis functions. So it's r1 phi 1 of x plus r2 phi 2 of x plus so on up to some rn phi n of x. So the important thing to remember is that phi I of x are known functions. They're just explicitly given functions. What are some typical choices? Phi I of x is x to the I. The most popularly used choice would be phi I of x is equal to x raised to the power I. So then what are you doing over here? You're just approximating Qt of x by a polynomial. You're simply saying, oh, x to the I minus 1, so that you allow the possibility of a constant. So then what you're saying here is that Qt is being approximated, so this is an approximation, by a polynomial. Choosing a polynomial is not always the right thing, but that's the most popular thing. So now what we want to do is propagate this thing via an iteration. So I want to combine this idea with that idea. So this is the idea of approximation. I'm approximating a function by some polynomial, just to fix ideas. Yes?
What's the difference between Vt of s and Qt of these?
This and that?
And the one below that. I mean,
This one?
Yeah. How is
Oh, there's just s is just a dummy variable. It's just s. It is a function. So whether I put x or s, it doesn't really matter. I need to know its value for the entire r plus.
Why are you shifting the Qt? Initially you were doing Vt was.
Why am I going from Vt to Qt? So as far as we are concerned, up to in this optimization course, this seems like a dumb idea. I mean, it doesn't really matter. If you can compute Vt, you can compute Qt, and if you can compute Qt, you can compute Vt. But what happens in practice, and here's the next slide, I'll come to it in a moment, let me answer this question, is that the way these things are computed is by simulation. So you simulate some n paths, and you're going to, what does that mean? That means that this expectation is never explicitly computed. This expectation is approximated by a sample average. And it makes a difference whether you're approximating and then taking a maximum, or you're taking a maximum and then taking an approximation. Numerically, there's a difference. So this is basically the story of the convexity problem.
You'll be sort of biased towards terms which are giving a return.
Exactly. So this one gives you bias, This one doesn't give you bias. This is a simple expectation. Some junk sitting in there. I don't care how this function was. It's a simple expectation. Once I know what this function is, it's simply I'm taking an expectation of that. I can take a sample average.
I think we're only seeing paths which actually give you a return in the second case. In the first case, you'll be seeing all the paths.
Not quite. You'll see all the paths, but it's just how you weight them. So when you're looking at the summation, it depends on what this is, right? If this is a 0-1 thing, then you're absolutely right. One you'll see paths and the other you won't. But this is more general. You could get some partial rewards along the path. Then all you're saying is that you're being optimistic here, and you're not being optimistic there. You're being neutral here. So numerically, it makes a difference whether you do that or this. From a purely theoretical perspective, they're equivalent. Okay? So this kind of mess will happen when you start doing practical stuff in financial engineering, that oftentimes you'll have equivalent ways of doing things theoretically, but practically they are very different because of certain other constraints that come into the picture. Okay, so what's our story so far? Let's not worry about how I end up getting this QT. So my story so far is simply that here's a recursion. It tells me that if I know the value of qt plus 1 as a function, I can compute what happens to qt. And I'm going to approximate qt by this. So what I want to do next is come up with an algorithm that will compute this and be able to allow me to use this approximation. So here's what this algorithm works. So typically what you do when you're trying to do using this approximate dynamic programming is that you compute n sample paths of the stock price. So you start from time 0 and you compute, here's time capital T. So here's time 0, time 1, time 2, time 3, time 4, time 5, and time capital T. That's equal to 6. So that's one sample path. It just tells you how the price evolved from time 0 to time capital T. Take another sample path. And a third one. So in your stochastics course, have you been told how to simulate Brownian motion and do various things with them? Yes? No? Okay. Whatever. I mean, essentially, if something is going through a Brownian motion or a geometric Brownian motion, simulating this is a fairly easy task. It's not a difficult task. All you have to do is generate a bunch of normal 0-1 random variables, multiply them with appropriate volatilities, add them up, and you get this graph. Okay? Now, what you do is you have to start back and do this recursion. So let's start and combine it with this approximation. So here's the story. What about qt plus 1? Q of t of s. What is the definition of this? By definition, what will it be? Q is the value that you get from not exercising but going forward. At time t, time capital T, the value of going forward is 0. So you assign a value of 0 to all of these points. Okay? You don't get any value. Then what you do is start from time t minus 1 backwards. This is the same iteration that we did. So start from time t minus 1. And what do you do at time t minus 1? At every stock price that you have. So here's the, let's remove this for the moment. So what you're doing is at time t minus 1, here are the possible stock prices. That's one, and that's one. So you've got n equal to 3 here. You compute the value of q t minus 1 evaluated at the sample 1 at time t minus 1 to be equal to the maximum of k minus s1 of t positive part and qt of s1 of t minus 1. There is no expectation going on here. All I'm saying is that at time t minus 1, look at the first sample path. S1 of t minus 1 is this quantity here. Here's S1 of t minus 1. Over the first sample path, you're getting S1 of t minus 1. This quantity here is S2 of t minus 1. This quantity here is S3 of t minus 1. You have three different samples for the stock price at time t minus 1. You compute what is the value of exercising at that cost. So this would be t minus 1. This is what you get by exercising at that sample point. This is what you get by going forward from that sample point. Okay?
Why is it in those street?
Which one?
From those you said it's t plus 1.
Which one? Yeah, so it's t minus 1 here and t minus 1 plus 1 there. So it's just this one? Oh, this should have been xt. No, not xt plus 1. And the same thing over here. Again, the important thing is that the details here are, I'll correct it and put it up there. The thing to remember here is this computation is done on a sample point. You've got another sample point here, so you compute that one too, qt minus 1, S2 of t minus 1. Again, the same formula, except that everywhere that you have 1, put 2. And then you have a third data point, qt minus 1 of S3 t minus 1 is equal to the max of the same thing at 3 t minus 1 and S3 of t minus 1. For every sample path that you have constructed, you get one value for this function. Okay? Now what you do is you solve this problem. Minimize summation of the sample paths, which are, let's say, I going from 1 through capital N, of q of t minus 1, s I of t minus 1. These are the values that you just computed, minus R1 phi xi of t minus 1 minus R2 of phi 2 of xi t minus 1 and so on up through Rn phi n of xi t minus 1. So this whole thing is the error at one of those data points. And you minimize this over the choice of R1 up through Rn. This is a simple minimum mean square error problem, or least squares problem. So you compute the solution of this, and now when you compute the solution of this, you get an approximation q hat of t minus 1 x, which is simply given by the optimum solution r star I phi I of x, I going from 1 through n. All right? So again, what am I doing here? I want to somehow combine the idea of the recursion with the idea of the approximation. Here's the recursion and there's the approximation, or a basics function expansion for the function. I want to combine these two somehow to have an iteration that goes backwards. So what do? I basically get the sample values by looking at the sample paths. So every time I do something, this q hat is a computation that is just done on the samples. These, I have capital N different values, there n is equal to 3, I get 3 different values. I take those 3 different values and compute what is the optimum constants by a regression procedure, which is the least squares problem. This particular, so this is in my notes over there, I call this q tilde, and these are all hats. So the q hats are just sample values. It's got nothing to do with the function right now. I sample the function at these locations, and this is what I expect to see. Then I solve the least squares problem to get an approximation. Now I plant back this approximation here and do the same thing for time t minus 2. And out here it's t minus 2 rather than t minus 1. Again, go through the same procedure and you get q tilde of t minus 2 and go backwards. Okay? All right. So at the end of the day, from this, what you're doing is a completely approximate procedure. You don't know how many sample paths you need to get a good approximation. All you're saying is, let's just generate n stock prices, some arbitrary number n. N better be reasonably large if you're trying to look at 3 data points, and if you're looking at polynomial functions here, let's not call this n, let's call this whatever, n tilde. If you are looking at n tilde numbers here, your n better at least greater than n tilde. Otherwise you get an overfitting problem. All kinds of horrible things happen. But so far, all we have said is that we've got a recursion idea, we've got this approximation idea, and we can recurse through to get an approximate solution. All right, so we've done all of this. And when you do Monte Carlo simulation, you will see how to do this more explicitly. Write a code to do it. But at the end of the day, what you end up getting is that you get an approximation for v tilde of 0, which is nothing but the maximum of k minus s0 positive part and q tilde of 0. Q tilde of 0 is something that I can compute and take the maximum of that with respect to the current price that I can get. I get an approximation for what the stock price is going to be, which is this quantity down here. The problem with that is that this particular quantity has no physical meaning. It's just some arbitrary thing that I did along the way. When I'm doing binomial trees, this number has a meaning. I am attaching with it an optimum solution. I'm saying when you're sitting at that particular node, do something. Either exercise or don't exercise. So corresponding to this number v tilde of 0, there is nothing concrete that I can say. So the way one can get around that problem is to have an first come up with an exercise policy. So the exercise policy in this case would be exercise at time t if q tilde of t is less than equal to k minus s t positive part. If the pros strictly less, let's say, if the cost of going forward or the reward from going forward is less than the reward that you get right now, just exercise. This is a policy. Q tilde is a function. I know this function explicitly because I have written it out as a combination of these basis functions. So this quantity here is known, that is known. So this policy is completely defined. What I can do now is find out what is the reward that this policy gives, again by simulation. So by simulation, compute the expected reward. Of this policy. And let's say that that quantity is v underscore 0. I just computed by simulation. For the moment, let's assume that simulation is such a interesting and established and easy tool that I say simulation, it simulates and gives me the answer. Otherwise, there's an entire course devoted to simulation, so clearly it's not that easy. But for now, let's just say simulate, and it outpops the answer. Now, what can you say about this quantity? Can you say that if the optimum solution is V0, what can you say is the inequality here? Is it a lower bound on V0, upper bound on V0, completely unconnected with V0? What can you say? So what I did was that I did some mess over here. I started out with this Q value, I did some approximation to the Q value, something which maybe makes sense, maybe does not make sense. At the end of the day, what I did was using that Q value, I came up with this exercise policy. At time t, you check what happens to the Q function, compare it with the revenue that you get from just exercising right now. If the Q function is less than the exercise value right now, just exercise it. I get a policy. So once I get this policy, I don't have to tell you how I got it. I went to sleep, got up, came up with this policy. Now I went and simulated it. And when I simulated it, this quantity is the reward that I'm getting from this policy. V0 is the optimum reward, it's the optimum way of exercising. Remember, V0 is defined in terms of that optimum stopping time, wherever it's there. There we go. So V0 is defined in terms of a stopping time which has time greater than or equal to 0. What can you say about the inequality there? So V sub 0 is a lower bound or an upper bound? Upper bound. Guys, we are trying to maximize something. We came up with some arbitrary solution that literally I'm pulling off of my hat. Not wearing one, but this has to be a lower bound. You can only do better than this. I have given you a particular stopping time. What? This is a stopping time. The policy is a stopping time. It's completely adapted. I gave you a function. I just said, here's the function. Compute this function anytime the stock price at this time, I'm not looking into the future, I'm just looking at the stock price at this point. I'm saying, evaluate this function. If this function is less than that function, stop. Completely a stopping time. There is, and
because when you write over there, it's not a stopping time because you have to know the future to stop.
No, you don't need to know the future. Stopping time says that you cannot have. So this tau, I have not written it there, but the tau is a stopping time. The only way you're only allowed to maximize this over stopping times. This quantity here, you know the distribution of the future, you don't know the sample path of the future. You're allowed to take decisions looking at the distribution of the future, but not looking at the sample paths in the future. At stopping time, you can do the same thing. You can look at what happened, the realization up to time t, at time tau, but the distributions going forward is okay. It's fair game. Oh, wake up.
I think the idea is that the stopping.
Oh no, come on. Anyway, doesn't really matter. Don't hibernate. All right. We can recover without that.
So what is the connection?
What?
What is the connection of this one and this thing?
Just a minute. Let me get this thing back up and then. What is the relationship between what and what? Would you repeat the question?
This formalism with the snail's envelope.
That's the next step. Will come in a moment. So what is the relationship between this and the Snell's envelope? Snell's envelope rather. So here all I'm claiming is this will give me a lower bound. How bad is this? So this particular story, in fact, this idea has been around for a reasonably long time. So at least through so Longstaff and Schwartz were the first people to come up with this idea of getting the bounds on, and that paper appeared in 1995. So I would imagine that at least 2 to 3 years before that, the idea was floating around. So this idea of trying to get a lower bound of the stock price has been around for a while. Now the question is, how do you get an upper bound? If you get an upper bound on this, then you end up getting a good localization for the value. You have an idea of how bad this lower bound is. The lower bound is achievable. There is a policy that gives you this value, but it could be really bad. This quantity is something that you cannot compute. You don't know what this quantity is. The only thing you know is this lower bound is achievable. So what you want to do now is get an upper bound. And for that, you use this technique. And this technique is due to Martin Haw, who is in this department, and Mark Brody, who is in the business school. So here's the idea. So you're looking at stopping times t greater than or equal to t, or greater than or equal to, and you're looking at the expected value of e to the minus r tau minus t of h of s tau. Let's just make it v of 0. I don't really care about anything else. So let's just call this 0. So any non-negative stopping time, and this is what this quantity is. So the idea that these guys had, and you can derive it many different ways. You can derive it using duality. Another way to look at this problem is to start with, let's say pi sub t is a super martingale. Also adapted to the same filtration. So what you do is add and subtract it. So let's say that this is equal to the supremum of tau greater than or equal to 0 of the expected value of e to the minus r tau h of s tau plus pi tau minus pi tau. Actually, let's subtract and add. I just added and subtracted a function, and therefore that doesn't change the value at all. Now I use linearity of expectations and say that this is equal to the supremum of tau greater than or equal to 0, the expected value of the first quantity, e to the minus r tau, h of s tau, minus pi tau, plus the expectation of pi tau. The supremum is outside, so far I've not done anything. Now I use optional stopping theorem to say that this supremum is upper bounded. So super martingale is a quantity that in expectation goes down. Therefore, this quantity V0 is less than or equal to this quantity. So instead of looking at pi tau, you look at pi 0. The expected value of pi tau is going to be less than or equal to the expected value of pi 0 because pi of t is a super martingale. You need to have certain regularity to make sure that the stopping time theorem goes through. Uniformly integrable is one of them, various kinds of other story. But something you need to here there is a gap. If pi of t is simply a super martingale, this won't go through. But you can put some regularity conditions such that this will go through. Okay? Now, what you do is you claim another thing that you can do is that this is less than or equal to the supremum of tau greater than or equal to 0, the expected value of the positive part of this. Right? Now what you end up getting from here is that this V0, the best possible upper bound that you can get, V0, okay, let's look at a few things when you're looking at this expression. The right hand side of the expression is a little bit messy because we have this problem that you still have to take the supremum over stopping time. But the nice part out here is that these are functions that you already know. There is no recursion going on. H is a given function, so you know what this is. Pi of t is something that you can choose. And therefore, at least you have gotten the problem of getting an upper bound on V0. You've reduced it to a problem of simply getting a stopping time. But still, that's exactly what we were trying to do in the first place. So we are not really gaining much. So what you do is do the next step. You say that V of 0 is less than or equal to pi 0, where pi of t is a super martingale, and pi of t, what happens to pi of t? Pi of t is greater than or equal to e to the minus rt h of s, this should not be pi t but pi tau, h of st. I only choose those super martingales which are lower bounded by this quantity. This is a quantity that's known. No stopping time anymore now. The stopping time has gone away from the picture. You choose any super martingale that you want which satisfies this constraint, then its value at time 0 gives an upper bound on the value of the option. Okay? Go one step further and say that this is in fact equal to the minimum of pi 0, because pi was a completely arbitrary super martingale which satisfies those constraints. So the best possible upper bound that I can get, yes?
I can get that. If you say that pi t is a super martingale,
Yes?
and then you say pi t is greater than or equal to e to the
Yes.
RT. Have we assumed at any point that e to the power of RT HST is, do we have any?
We don't care.
We don't have any assumptions?
No, nothing.
Okay.
It's just some function, some arbitrary function that's given to me. All I'm saying is pi t is a super martingale. It should come down in expectation.
Yeah, but what if e to the power of RT HST is martingale, or is it if it's sub-martingale?
So if it's sub-martingale, then you get a very bad bound. So then pi of t has to be greater than this sub-martingale, which means that it has to be greater than the last quantity, which means that it basically has to be really, really high up.
It has to be an extremely large bound.
It has to be an extremely large bound. But the bound, nevertheless, it is. I'm not saying what the quality of this bound is, but bound, nevertheless, it is.
But what if the submartingale is closable?
What?
What if the submartingale has a less element, which is finite? So can you still bound that?
Yeah, you can do all. I mean, the tricks. You can play all kinds of different tricks here about what you can separate it out. You can write it out as a one of those a plus m. What is a? Bounded variation function plus a martingale or whatever. You can do all kinds of tricks. My point simply of showing you this exercise is to show that I didn't have the time to show you that what is happening here, this whole exercise here, is basically I'm taking the dual of the linear programming representation of the dp. There's a linear programming representation, and you can convince yourself, and if you are interested, I can show you offline, that this stuff, all this computation is nothing but computing the dual linear program. And what you end up getting from here is that now you can start computing bounds. Take any super martingale which is lower bounded by this discounted process, take the minimum value, take the value of it at point pi 0, and you get an upper bound. So you get an upper bound for any value of pi.
So the first part is bounded by 0.
Upper bound, just a minute, for any choice of pi. Yes, question?
Yeah, I mean, the first term is bounded by 0.
First term, which is, what do you mean by first term?
Should swim by expectation.
Part of the expectation.
Oh, this is just, this is bounded by 0, but this could be negative. I've done an approximation from going from here, therefore you have another inequality there. It turns out that this inequality is in fact an equality. And this particular story here is called this pi star is called the Snell's envelope. It is the smallest super martingale that dominates over the discounted price for current execution. Okay. So what you end up getting from here is you end up getting an upper bound. Something. For every choice of pi, you get an upper bound on V0. Somebody needs to keep track of time. I don't have time anymore. It's over? Okay. So just one more little idea and then I'll let you go, which is this. One thing, so this is something which is achievable, but remember this upper bound is not achievable. The fact that you're creating a super martingale doesn't mean that this upper bound is achievable. And clearly it cannot be because it's an upper bound over V0, so you cannot achieve this thing, but at least it gives you something in between. And now the nice thing that Martin Haw and some other people have found out is you can actually iterate from this point to that point and that point to this point. Meaning you get a policy, meaning you get a Q tilde. Using the Q tilde, you compute a good super martingale, which comes from V tilde. And if you're interested in how you compute the super martingale, go look up Martin Haw's website, and there's a reference to his paper which shows you how to do this. So you compute a good pi. Given a good pi, you can compute a good policy, which means that you can start pulling this lower bound forward. You get a better lower bound, you come back and compute a better pi and go back. And every time you do this, you can start improving. Doesn't mean that you're going to converge to V0, but at least it gives you a way of improving from what was an initially perhaps bad bound to a better bound. There's no reason to believe that this bound is going to will keep on improving, but locally it does better. All right, so that finishes whatever I want to teach in this course, and we'll see you again on Thursday morning. I'll be available here for any questions, And on Thursday afternoon, we'll have the final exam. Thanks.